Welcome to The Explainer. Today, we're going to tackle a concept you probably think you know inside and out, acids. But as we're about to see, the real definition is way more complex and, honestly, more fascinating than what you probably learned back in high school. Okay, but before we jump in, just a quick heads up, this is going to be a more technical look at the chemistry here. If you're looking for the basics, we've actually got a great introductory explainer on the channel that'll set the stage perfectly for what we're covering today.
You know, we run into acids all the time, from the citric acid in a lemon to the hydrochloric acid churning in our own stomachs. They can be harmlessly delicious or, dangerously corrosive. To really get why, we need to dig into the fundamental chemical definitions that actually control how they behave.
So let's start at the very beginning, with the first real formal definition that gave chemists their initial blueprint for understanding these things. So this Swedish scientist, Svante Arrhenius, came up with a really simple but powerful idea. He said an acid is basically any substance that, when you dissolve it in water, releases a positively charged hydrogen ion. Now, since a hydrogen atom is just one proton and one electron, an H+ ion is, well, it's literally just a naked proton. And look, this definition, it works beautifully for a ton of common situations, like hydrochloric acid in water. But you know how science is, right? It's all about pushing boundaries. And chemists pretty quickly found out this simple rule had its limits. It just couldn't explain every observation, which of course led to the first big evolution in our understanding. And that limitation? Well, it led to a pretty major puzzle.
See, some chemicals were clearly acting like bases, the chemical opposite of acids, but they just didn't fit into that neat Arrhenius model at all. This was a real head-scratcher for chemists. Take baking soda. It can neutralize an acid. That's a classic base move, but it doesn't produce hydroxide ions in water. This exact problem is what led two scientists, Johannes Bronsted and Thomas Lowry, to each come up with a more flexible, more action-oriented definition. This is where it gets really clever. Instead of focusing on what an acid produces, Bronsted and Lowry zeroed in on what an acid does. An acid is a proton donor, and a base, then, is simply a proton acceptor. It's an elegant shift that reframed the whole thing from a static property to a dynamic give and take. And this diagram right here, it's a perfect visualization of that handoff. The acid, HCl, gives its proton to the water molecule, but in doing that, the acid becomes what we call a conjugate base, and the water, now that it's accepted the proton, becomes a conjugate acid. It's all about these chemical partnerships.
So what you're seeing here is just how big of a leap in understanding this was. The Bronsted-Lowry theory basically unshackled the definition of an acid from water. Suddenly, acidity could happen in any solvent, and the definition of a base became this perfect logical counterpart. One gives, the other takes. But chemistry wasn't done yet, not by a long shot. What if a reaction looked and acted acidic, but there were no protons involved at all, no hydrogen to even donate? This question pushed the definition to its most fundamental and its most abstract level. This is where the great chemist G.N. Lewis comes in, and he proposes what is hands down the most all-encompassing definition yet. He completely shifted the focus away from the proton and onto the most fundamental particle in all of chemical bonding, the electron. A Lewis acid is simply anything that can accept a pair of electrons to form a bond. So think about it. We've kind of zoomed out completely here. The Bronsted-Lowry model is all about the movement of a positive charge, the proton. The Lewis model is all about the movement of negative charge, a pair of electrons. The base donates the pair, the acid accepts it. This simple idea covers a massive range of reactions that the other theories just couldn't touch. Okay, so this table really brings it all together, right? It's the perfect summary of our journey. We started with Arrhenius, the strictest definition, totally stuck in water. Then we expanded with Bronsted-Lowry, focusing on that portable proton. And finally, we landed on Lewis, the broadest, most fundamental definition based entirely on how electrons behave. Okay, so we've got all this great layered theory, but how does it actually connect back to the real world? Why is the acid in your stomach so different from the acetic acid in, say, vinegar? Remember that hydronium ion, the H3O+ we saw earlier? Well, that's the real culprit behind an acid's fearsome reputation when it's in water. A free proton is so reactive, it instantly gloms onto a water molecule, forming hydronium.
This new ion is incredibly unstable and just desperately wants to get rid of that extra proton, so it'll aggressively try to pass it to almost anything it bumps into.
And this is where we get to a really key concept, acid strength. And it's probably not what you think. It isn't really a measure of how dangerous an acid is. It's actually a measure of how willingly it gives up its protons in a solution. It's all a numbers game. What percentage of the acid molecules actually go through with donating that proton? Just look at this chart. It shows the difference perfectly. A strong acid, like the hydrochloric acid in your stomach, almost completely dissociates. We're talking nearly 100% of its molecules donate their protons. That creates a really high concentration of those reactive hydronium ions. But a weak acid, like the acetic acid in vinegar, is way more stingy. Less than 5% of its molecules actually dissociate, so you get far, far fewer hydronium ions. I mean, think about it. From the carbonic acid making your soda fizzy, to the sulfuric acid that powers your car, to the citric acid in your orange juice, these molecules are absolutely everywhere. And each one has a different structure, a different tendency to donate protons, and that's what dictates its strength and its role in our world. And just when you think you've got it all, there's one more layer of complexity. Some acids are extra generous. They have more than one proton to give away. Sulfuric acid is diprotic. That means it can donate 2 protons, one after the other. And phosphoric acid is polyprotic, meaning it can donate 3. Each one of those donations is a separate chemical event, which just adds even more richness to how these things behave.
All right, so after that whole deep dive into this complex, evolving definition, what are the really crucial points you need to lock in to understand all this?
These 5 pillars really give you the whole picture. Number 1, science is a process. The definition had to evolve. 2, the most common everyday definition you'll use is the Bronsted-Lowry proton donor. 3, the most fundamental, big picture definition is the Lewis electron pair acceptor. 4, strength is all about dissociation, not danger. And 5, in water, that reactive hydronium ion is the real star of the show. And of course, even though we've talked about acids found in the human body, please remember this explainer is for educational purposes only. You should always consult a medical professional for any real health concerns. You know, this whole journey really leaves you with a fascinating final thought. We just saw that even a supposedly simple concept like an acid is built on these layers of increasing abstraction and complexity. It really makes you wonder, what other fundamental scientific ideas that we just take for granted are actually just the first chapter in a much, much deeper story?